In this part of this lesson, under atomic structure, we will discuss in detail how electronic configuration is written for different elements. Electron configuration of an atom shows how electrons are arranged in quantum numbers. Quantum numbers means energy levels. By organizing electrons in quantum numbers, repulsion among electrons is minimized. It means when electrons are arranged in an atom, these electrons should stay far away from each other as far as possible, because if electrons come closer, the negatively charged electrons will try to repel each other, and the atom will be highly chaotic and it will be highly disorganized. Lots of electrons will be seen moving here and there because they repel each other. No, it's not like that. Electrons have been observed to arrange in particular areas in energy levels and orbitals, as we discussed in the previous lesson. But how exactly are we going to write the electronic configuration? We have discussed about this before also. However, when you add electrons or when you write electronic configuration for an atom, there are several rules, but I have condensed these rules to 3. First one, when electrons are added to an atom which is devoid of electrons, that means it doesn't have any electron, first electrons go to the lowermost energy level. Second rule, electrons are added to the higher energy levels only after the lower energy levels are fulfilled. It means you can't go to second quantum number without filling the quantum number 1. You can't go to quantum number 4 without completing quantum number 3. Okay. Rule number 3. While filling degenerate orbitals, you have to write under degenerate orbitals. You can write here, orbitals having the same energy. Under rule 3, while filling degenerate orbitals, underline degenerate orbitals and write orbitals having the same energy. Okay. Pairing of electrons in an orbital start after all orbitals get at least 1 electron. That's in degenerate orbitals. Okay, let us discuss about these things in detail once we start writing this electronic configuration. You can write electronic configuration under 5 types. First one is Spdf notation. Second one is shorthand method. Third one is box notation. Fourth one is general after configuration. Fifth one, energy level diagrams. There are 5 things, 5 methods of writing electronic configuration. We will write the electronic configuration for atoms in Spdf notation. We have a big diagram over here. Okay. Without talking about this diagram, I will discuss about writing electronic configuration in Spdf notation. You should know why we say Spdf notation. There's a reason for that. To explain this, let me take this. If I write electronic configuration for these atoms, I'll take one example. Let's say beryllium. Beryllium has atomic number 4. Atomic number 4 means there are 4 protons and 4 electrons also. How are these electrons arranged? Do you remember the first rule I told? When orbitals get electrons, first they should go to the lowermost energy level. In this arrangement of orbitals or energy levels, the lowermost energy level is quantum number 1. Quantum number has 1s subenergy level. It has only one orbital. So from these 4 electrons, the lowermost energy orbital is 1s. So you write 1s. 1s means in the quantum number 1, subenergy level is s. There we can have beryllium has 4 electrons, but 1s can have only 2 electrons. So you write 1s2. It means in the 1s orbital, we have 2 electrons. From 4 electrons, when you give 2 electrons are remaining. After filling electrons in 1s, next electrons come to 2s. 2s has how many electrons? 4 minus 2, 2. But how do you write this in O level? In O level, we write 2, 2. 2 is actually the 2 electrons in the 1s subenergy level. Second 2 means 2 electrons in the second subenergy level. Now I go to oxygen. Oxygen has 8 electrons. Of course, it has 8 protons and 8 electrons. Now, are we going to write the electron configuration for oxygen according to O-level method, A-level method? Okay, when 8 electrons are added, first electrons go to the lowermost energy level in an atom, which is 1s. So you write 1s. 1s how many electrons? 1s can have 2 electrons. I have 8 electrons. I can keep 2 electrons here. After adding electrons in 1s, next we go to 2s. This is 2s. It is s orbital. S subenergy level has 1 orbital. S subenergy level can have how many electrons? 2. 1s has 2 electrons. 2s has 2 electrons. After adding electrons in 2s, we go to 2p. What is the maximum number of electrons you can have in p? P can have maximum 6 electrons. P can have maximum 6 electrons. But from 8, when you give 2 electrons here and 2 electrons there, 4 electrons are removed from 8, 4 electrons are remaining, we write 2p4. But in O level, we write 2a. Why 2a? No, 2,6. But write 2,6. 2,6. It is because in the first quantum number, 2 electrons are there. Second quantum number is 2 plus 4, 6. Now I take sodium. Sodium has 11 electrons. Because it has 11 protons, it also has 11 electrons. But you do first, from these 11 electrons, first you take 2 electrons to 1s. 2. And then 2s. 2. How many electrons have you kept? 4 electrons. We have started with 11 electrons. Now 4 electrons taken. After 2s, you go to 2p. Do we have enough electrons? Yes. 2p can have maximum 6. Now 2 plus 2 plus 6, it is 10. We have maximum of 11 electrons. 1 is remaining. After 2p, where do we go? 3s. 1. In O level, we write 2, 8, 1, the electronic configuration for sodium. Why? This is 2, 1 is 2. 2s, 2p means second quantum number 8. Third quantum number 1. Let's try to find out the electronic configuration of 1. It is chlorine. Chlorine has atomic number 17. It means it has 17 protons and 17 electrons also. So if you write electronic configuration for 17 electrons, now you should be familiar with this. First, you take electrons to 1s. 1 is how many electrons? 2 electrons. After you add electrons to 1s, you go to 2s. 2s can have maximum 2 electrons. After 2s, we go to 2p. 2p can have 6 electrons. We have plenty of electrons. After 2p, we go to 3s. 3s2. After 3s, we go to 3p. This is 3p. How many can you keep in 3p? To know that, you just count the number of electrons and see. Here, chlorine has 17 electrons, but I have written already 2 plus 2, 4 plus 6, 10 plus 2, 12. Out of 17, when 15 electrons are taken away, yeah, you take 15 electrons away, you are left with 5 electrons. So we can write 5. This is the electronic configuration of chlorine. Because I'm showing where electrons are present orbital-wise, 1s, 2s, 2p, 3s, 3p. This electronic configuration writing method is called Spdf notation. This is called Spdf notation. Why do we call it Spdf notation? Because in our electronic configuration, I write in detail where exactly electrons are in what sort of orbitals in S, O, P, O, or F. This is how we do the electronic configuration for elements in Spdf notation. This is very simple. If anyone wants to make a note of this, I can give a couple of minutes. Even though I have shown the electronic configuration writing for a couple of atoms like beryllium, oxygen, sodium, and chlorine, you will have some difficulties when you write electronic configurations upwards in this chart. Why? Because there are some overlappings happening. If you go on writing electronic configuration, first you add into 1s, then you add into 2s, 2p, 3s. After 3s, you will go to 3p. But without going to 3d, you will have to come to 4s because there's an overlap. Right? It's extremely difficult to write electronic configuration further upwards. So for that, the scientists have found out a method, and we had to follow this method. Some orbitals show overlapping. Some orbitals show overlapping. Hence, to construct electron configuration, taking this overlapping pattern into consideration, the following electron filling chart must be remembered. First, this chart will never be given to you in the exam. It doesn't come in the paper, not in the data booklet. So you have to write this. Writing this electron filling pattern is not a very difficult thing. It's easy. We'll try to construct, even though it's given over here, we'll try to construct this electron filling chart, we say. Electron filling chart separately. This is how we start this work. I will write the writing mode, typing mode. You start with the first quantum number, okay? 1s. After 1s, we go to second quantum number. Second quantum number has 2s. Remember the other one, 2p. Afterwards, we go to 3s, third quantum number, 3s, 3p. After 3p, what comes? 3d. 3s, 3p, 3d. And then we go to fourth quantum number, 4s. In the fourth quantum number, there are 4 sub-energy levels, 4d and 4f. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Now we go to fifth quantum number. There we can write 5s, 5p, 5d, 5f. We don't write more than f. 5f is enough. And you go to sixth quantum number. 6s, 6p, 6d. That's enough. We don't have to go to f. And then 7s, 7p. Don't go to 7d because we don't have that many electrons in atoms to fill. Next, we go to 8s. First, you draw the structure. And then the electron filling pattern can be found out if you draw diagonal lines. And diagonal lines which are parallel to each other. How? If you draw one line here, 1s, next one is across 2s, and then 2p, 3s. See the order. 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, and then another line over here. Definitely, I know that there are some children who are looking at this in a kind of a very, very weird manner. Oh, this is difficult. Okay, after you construct this chart, what you must do is go to the bottom of it and there draw a line connecting all these finally appearing orbitals in this manner. And then afterwards, if you draw parallel lines to these things, one comes here. And redo it. It's a matter of just drawing parallel lines in this manner. It's easy. And then we are starting with the topmost line. First electron addition occurs in 1s. So when you write electronic configuration, first line comes to 1s. So electron addition occurs in 1s first. Now come to second line. Second line, it goes through 2s. That means next electron come to 2s. So we write 2s after 1s. So this line is over. We go to third line. Third line, first the line cuts through 2p and then 3s. So 2p, 3s. After the third line, we go to the fourth line. In the fourth line, we have 3p first, 4s next. So we can write 3p, 4s. That's how electrons are arranged. If you want to do further, then we come over here. It is 3D. You write 3D and then 4p and then 5s. Likewise, you go on drawing writing electrons in the electronic configuration. Now you can see this chart. I have done everything. What we have to do is to draw lines. How? Draw a diagonal line. I can't draw properly. You can take a ruler and do it. Okay. First electron addition occurs in 1s. Second one is 2s, 2p, 3s, 3p, 4s. Then 3d, 4p, 4s, it goes like that. First you complete these lines, parallel lines. From here, we go to the writing electronic configuration. Use the above electron filling chart to construct the electron configuration of the first 20 elements in the periodic table according to Spdf notation. Hydrogen, for example, is having only one electron. So we can write 1 is 1. Helium, only 2 electrons are there. 1 is 2. Lithium has 3 electrons. So we can write 1 is 2, 2 is 1. There are 3 electrons. Likewise, can you write the electronic configuration up to the 40th one? 20th element. 20th element means until potassium. Okay, I'll give a couple of minutes to do that. Start doing the work. One minute, children, when you draw this electronic configuration, first you complete the electronic configuration of one element completely. After complete beryllium configuration, you can come to boron. So that's how you have to do it. Otherwise, you don't learn anything from this lesson. Okay, go ahead. Let's see how we can write the electronic configuration for other elements also, according to Spdf notation. Beryllium. Beryllium has 4 protons, means 4 electrons. So I can write 1s, 1s2, 2s, there are 4 electrons, so 2s2. That's the configuration for beryllium. Boron has 5 electrons. 1s2. Afterwards comes 2s. 2s also can have 2 electrons. From 5 electrons, 4 electrons have been used. After 2s, from the chart, we can get 2p. 2p, 1 electron. Boron configuration is 1s2, 2s2, 2p1. Children always see the digit before the sub-energy level. S. Before S, we have 1. This 1 shows you the quantum number. And the number of electrons in that quantum number is written on the right-hand side in superscript form. Now come to carbon. Carbon has 6 electrons. Of course, what you see is the protons, but proton number is equal to electron number. So we can write electronic configuration for 6 electrons in Spdf notation. 1s2, 2s2, 2 plus 2, 4 electrons are used up. 6 electrons altogether. So 2 more electrons remain. I write 2p2. When I go to nitrogen in that manner, 7 electrons, 1s2, 2s2, there are 3 more electrons remaining. So you write 2p3. P subshell can have maximum 6 electrons. Next one, oxygen, 8 electrons. 1s2, 2s2, 2p, we can write 4 electrons because P can have maximum 6 electrons. Now go to fluorine. 1s2, 2s2, how many electrons are remaining? 5. 2p5. And for neon, 10 electrons. I can write 1s2, 2s2, 2p6. I have filled the p orbitals with the maximum electron number they can have. Now sodium. Sodium is 11 electrons. 1s2, 2s2, 2p. You can't write 7 because p can have maximum 6 electrons. So you can write 6 over there. 2 plus 2 plus 6 is 10. 11 electrons are there. So afterwards we go to 1s2, 2s2, 2p, 3s. 3s, 1 electron. Magnesium, 12 electrons. 1s2, 2s2, 2p6, I can have 3s2. Now we go to aluminium, 13. 1s2, 2s2, 2p6, 3s. You can't have more than 2 electrons. So you write 3s2 and next electron goes to 3p1. We have 13 electrons, 2 plus 2, 4 plus 6, 10 plus 3, 13. Silicon, 14 electrons. 1s2, 2s2, 2p6, 3s2. How many electrons are remaining more? 2 electrons, so 3p3, 3p2. Phosphorus has 15 electrons, 1s2, 2s2, now there are 4 electrons, 2p6, there are 10 electrons, 3s2, there are 12 electrons, 3 electrons are remaining, so 3p3. Write each and every electronic configuration as a fresh one. 1s2, 2s2, 2p6, 3s2, 3p. There are 4 electrons remaining. Next one. 17 electrons. 1s2, 2s2, 2p6, 3s2, 3p. There should be 2 plus 2, 4 plus 6, 10, 10 plus 2, 12, 5 electrons. Argon. 1s2, 2s2, 2p6, 3s2, 3p6. Okay, we have filled the maximum number of electrons for the p subshell, 3p. I asked you to write the electronic configuration for the first 20 elements, but I have done only first 18. Well, afterward, there's some notes to look at. There is a disorganized arrangement in orbitals afterwards, after argon. This occurs because when energy levels come closer away from the nucleus and their branching increases, certain sub-energy levels tend to overlap. I explained this to you very clearly in the last lesson, so you will not have difficulty. Tend to overlap with those of neighboring shells. Note is asking us to go to page number 4. We'll go to page number 4 and see what it is. See this diagram. In this diagram, we can see 1s, 2s, 2p, 3s, 3p, 3d. Below 3d, we have 4s. This is the first overlap. So from this point upwards, there are so many other overlapping patterns, but we don't have to think about the overlapping pattern from this diagram because we have found out an electron filling chart. Remember, electron filling chart. We discussed about the electron filling chart. With the help of it, we can overcome this difficulty. Where's the electron filling chart? Yes, this one. All right, now come to our next part of the lesson. There is a disorganized arrangement in orbitals afterwards. This occurs because when energy levels come closer away from the nucleus and their branching increases. Certain sub-energy levels tend to overlap with those of neighboring shells. See page 3. Make it 3, not 4. See page 3. This is called overlapping of orbitals. The first orbital overlap occurs between 3d and 4s. We just had a look at it. Accordingly, electronic configurations take a different form starting from scandium due to orbital overlap. 4s orbitals get electron before 3d orbitals because 4s is low-lying orbital than 3d. Okay, we have to talk about this after this potassium and calcium. Still, we have not come to that point. So we'll write for for potassium, electronic configuration for potassium. Shall we do it? 1s2. Don't think about this lesson I talked about now because it will be after calcium. 1s2, 2s2. You should know this by heart now. 1s2, 2s2, 2p6, 3s2, 3p6. After 3p, 1s2, 2s2, 2p6, 3p. Now, how many electrons have been assigned here? 2, 2, 10. Now, 18 electrons are there. Now, we want to go to the remaining electron. After potassium has 19 electrons. I have written 18 electrons. After 3p, where can I go? Can I go to 3d? No, you can't go to 3D. Actually, 3D is coming after 3p in the third quantum number, but because of electron overlapping, after 3p, electrons go to 4s, 4s1. Likewise, when it comes to calcium, 20 electrons, 1s2, 2s2, 2p6, 3s2, 3p6. After 3p6, where should you go? 3d. But we can't go to 3d because due to overlapping, 4s has come below 3d. So we have to have 4s2. This is how we write electronic configuration for potassium and calcium. Shall we go to the electronic configuration of the next one now? 21, scandium. Scandium. There is a note. After the addition of all the electrons to an atom, the orbital sequence has to be changed to make sure that orbitals arranged in the proper sequence, starting with the lowest energy orbital. We'll see what this talks about here. It's a special note. Let us not talk about it very much. I will take an example and say, scandium is 21. 21 electrons. We can write the configuration 1s2, 2s2, 2p6, 3s2, 3p6. After 3p, what is the next orbital? After 3p, we go to 4s. Let's see the electron number remaining. 2, 4, 10, 12, 18. This one gets 2 electrons, so it makes 20 electrons. You can't have more than 2 electrons in 4s. In the filling chart, what is there after 4s? After 4s, you go to 3d. After 4s, you go to 3d. So we write the electronic configuration here, 3d. 1 electron is remaining, so 3d1. This is how we write electronic configuration according to filling pattern. This is a filling pattern, but exam will not accept this as an electronic configuration because filling pattern is actually different to electron configuration. We have to construct this electronic configuration, electronic filling pattern. We have to reconstruct electron configuration using filling pattern. This is how the electronic configuration is written in the exam. 1s2, 2s2, 2p6, 3s2, 3p6. Don't write 4s, write 3d. 3d1, 4s2. We remove the 4s2 to the last position and bring the 3d inside, because then we can have them in order 1, 2, 2, 3, 3, 3, 4. But in the filling chart, we have 1, 2, 2, 3, 3, 4, 3. So this is kind of a disorganized manner. In the exam, we don't write this first one because it's wrong. You have to write the second one. This is an accepted electronic configuration for the exam. I write for titanium now. 1s2, 2s2, 2p6, 3s2, 3p6. After 3p6, we go to 4s2. 4s2. After 4s2, we go to 3d. I think there are 2 electrons. But here the sequence of quantum numbers is a big mess. So we don't write this for the exam. For the exam, we write 1s2, 2s2, 2p6, 3s2, 3p6, bring 3d2 inside and 4s2 out. This is an accepted electronic configuration. Shall I write the electronic configuration for the next one? Vanadium, this is vanadium. It has 23 electrons. 1s2, 2s2, 2p6, 3s2, 3p6. After 3p6, we go to 4s. 4s2, and we have 3d3. And the correct electronic configuration accepted by the examiner is 1s2, 2s2, 2p6, 3s2, 3p6. Bring 3d in. 3d, it should be 3, yeah, and 4s2. This is accepted electronic configuration. Vanadium is wrong. Okay, we have written the electronic configuration up to vanadium. That means we have covered 23 elements. Everything is okay until now. Of course, there is a bit of confusion in the scandium, titanium, and vanadium, because when you write the electronic configuration according to filling pattern, you get one configuration. But I said in the exam, you can't write it. For the exam purpose, we had write the second line, where the quantum numbers have been rearranged to show the sequence of quantum numbers. Afterwards, we go to small point. Important, very, very important point. I'll give you 2 minutes to read this. This is important. Please read it first. What this note tells is this. When you write electronic configuration, there are some situations where you have to rethink several times before you come into a final conclusion. At this point, what we must remember is this. If electron arrangement of an atom is well done, well organized, then an atom is going to be stable. Okay? The stability of an element is decided by the electronic configuration. In certain cases, we have seen electronic configuration in this manner. We have 3D. When you write electronic configuration, always remember, we saw over here, in the electronic configuration, we write 3D is appearing first. 3D is appearing first. 4s comes afterwards. 3D, 4s, 3D, 4s. Can you see in all these electronic configurations, we have here 3D1, 4s2. Here we have 3D1, 4s2. Here 3D2, 4s2. Here 3D3, 4s2. 4s2 is remaining constant. 4s2, 4s2, 4s2. But 3D electron number is increasing one by one. 3D1, 3D2, 3D3. Okay. If I take this diagram into this, suppose there is an element with 3D4 and 4s2. Or else we have 3D9, 4s2. What is special about this 3D4 and 4s2 and 3D9, 4s2? The speciality is this. 3D. Try to recollect how many orbitals are there in 3D subshell. How many? 3D has how many orbitals? 3D subshell or sub energy level has 1, 2, 3, 4, 5 orbitals. And outside we have 4s. If I take the same picture to the next one also. Let's try to find how electrons are organized in these orbital sets. In the first one, there are 4d electrons. I will draw the 4d electrons. 1, 2, 3, 4. 4s2 electrons are there here. And here we have 3d9. 1, 2, 3, 4, 5. And then 6, 7, 8, 9. 4s2 means 2 electrons are there. Now, what is special about this? I can write 3d4. 3d4 need a 3d4 arrangement. 3d4 arrangement needs one more electron to make it 3d5. All right. 3d4 arrangement needs one more electron to make it 3d9. 3d5. 3d5 means the 3d5 means the degenerate 3d5 means a degenerate orbital set is half complete. It is half complete if a d orbital set is half complete, comma, the element is stable. Got that idea? We have 3D4. And what I'm telling is 3D5 means the degenerate orbital. Oh, wait a minute. 3D4 arrangement needs one more electron to make it 3D5. 3D5 means the degenerate orbital set is half complete. If a d orbital set is half complete, the element is stable. Likewise, I will go to the next one. And I can rewrite 3D. Here we have 3D9. 3D9. Wait. 3D9 arrangement. Needs one more electron to make it 3D10. 3D10 means the degenerate orbital set is completely stable. The degenerate orbital set is completely stable. That means element is stable. All right. What you must remember is this. If you have 3D5, then it is half complete. Element is stable. If it is 3D10, orbital set is completely stable. It is stable. Okay, and now according to this theory, now look at this. Here we have, let me take this again. See here. Because we have 3D4, from this 4H2, one electron is taken. From this 4H2 also one electron is taken. If you take that electron, the electron arrangement changes now. How will it change? Here we get 5 electrons. Here we get 10 electrons. And this electron goes out. This electron also goes out. This one is stable. Therefore, whenever you see 3D4 4s2 configuration or 3D9 4s2 configurations, they will change. How? From the 4s2 orbital electron, one electron is taken to 3D4. So 3D4 is going to change to 3D5. 3D5 is stable. And 4s becomes 1. Here, 3D9 gets 1 electron from 4s2. So 3D9 becomes 3D10. And this will be just 4s1. 3D10 is more stable than 3D9. 3D5 is more stable than 3D4. So elements undergo a rearrangement in their electronic configuration to become stable. Hope you got the idea. Now see this. Certain atoms undergo an internal rearrangement in their electronic structure for better stability. This occurs in atoms where the number of electrons in the D subshell is either 4 or 9. I said D4 or D9. If D4 configuration changes to D5, then all the D orbitals in the degenerate orbital set get at least an electron each. This is called a half-complete d orbital set. A half-filled d orbital set shows an extraordinarily high stability. Hence, an atom having this type of configuration undergoes a change as shown below. Yeah? N-1 d4 NS2 goes to N-1 d5 NS2. Now this is half stable. If D9 configuration changes to D10, then all the d orbitals in the degenerate orbital set gets 2 electrons each. This is called a complete d orbital set. A completely filled d orbital set shows an extraordinarily high stability. Hence, an atom having this type of configuration undergoes a change as shown below. N-1 D9, NS2 goes to N-1 D10, NS1. Okay. This configuration, electronic configuration variation or changes happening for better stability can be discussed using chromium, manganese, iron, cobalt, nickel, copper, and zinc as well. Children, here you have to change this zinc to 30. I have given as 31. Make it 30. Zinc must be 30. I will write the electronic configuration for chromium. If you write the electronic configuration in electron filling pattern, we can see 1s2. Can you complete for chromium here? Manganese, iron, cobalt, nickel, copper. Yeah, without wasting time, quickly do it. I'll give you 4 minutes for this. Please do it first. We will see how you have written the electronic configuration now. Chromium electronic configuration is I will end this session here and start another session for the next part.